Section 3.1 Introduction to Determinants. Here's some notation. We have a matrix A with a subscript ij, and that is our matrix obtained from matrix A by deleting the ith row and the jth column of A. So let's look at an example here. Here's my matrix A, and I want to identify what A subscript 2, 3 would be. So what that means is that I'm going to delete the second row from my original matrix A, and then I'm going to delete the third column from my original matrix A. And so I've now got a 3 by 3 matrix, which is 1, 2, 4, and then 9, 10, 12, and then 13, 14, and 16. And so this is my matrix A sub 2, 3. You should recall that the determinant of a 2 by 2 square matrix ABCD is equal to AD multiplied together minus BC multiplied together. And we let the determinant of a matrix with just a single entry be equal to the number that is that entry. Here's a definition. For n greater than or equal to 2, the determinant of an n by n matrix A equal to A sub ij is given by the following formula. The determinant of A is equal to our little a sub 1, 1, which is the entry in that location of our matrix, multiplied by the determinant of the matrix that we get from deleting the first row and first column, minus then our second entry A, 1, 2, times the determinant that we get from deleting the first row and second column, plus, and notice that we're alternating signs here. We started with minus, then plus. So what we've got here is negative 1 to the 1 plus n. And we'll look at another way to easily determine your signs here in a minute. This all boils down to this formula here, which is a summation, and you notice the sign is occurring here where j is our column, and so the sign is alternating, and then we're multiplying the number in our matrix position times the determinant of the new matrix we get when we delete that row and that column that entry was in. So let's look at an example. It'll make that easier to understand. We want to compute the determinant of this, and what we're going to do is we're going to strictly stick with the first row of this matrix. So we're going to find the determinant of A, and we're going to take our very first entry, so that would be 1, so that's A sub 1, 1, and we're going to multiply it by the determinant of A 1, 1, which is going to be the matrix that we get when we basically delete that first row and first column. And so we're taking the determinant of negative 1, 2, 0, 1. And we're going to subtract 2, this next entry in our row, and we're going to multiply that by the determinant of the matrix that we get when we delete the first row and the second column this time. So we have 3, 2, 2, 1. Then we're going to add, we now have 0 as our entry, and we're going to take the determinant of our matrix when we delete the first row and the third column. So we have 3, negative 1, 2, 0. So for this example, you'll notice that I wrote these in matrix notation and wrote out the word determinant, but from now on I want to look at kind of a common notation for a determinant, and so this will enable us to do a little less writing from now on. When I take the determinant of a matrix A, B, C, D, and my matrix written with my brackets here, I can just simply write it with bars, kind of like absolute value bars looking, and have my matrix inside. And when I write this, it means that I want to take the determinant of what's inside of it. So we could rewrite this then, the determinant of A, we would just rewrite the matrix A inside these bars. And that notation would tell us we want to take the determinant of that. And so what we have then is our first entry times the determinant of negative 1, 2, 0, 1 minus then 2 times the determinant of 3, 2, 2, 1 plus then 0 times the determinant of 3, negative 1, 2, 0. So we need to find these individual determinants of these 2 by 2's, which means we're going to cross multiply. So here I have negative 1 minus 0. If I do this one, then I have 3 times 1, which is 3, minus 4 here. And then here I'll have, cross multiplying, 3 times 0 is 0, minus a negative 2, which makes it a plus 2. So what I've got then is 1 times what we get here, which is negative 1, minus 2 times negative 1, plus 0 times 2. So I have negative 1 minus a negative 2, which is plus 2, and then plus 0. So we end up with then getting 1 for our determinant of A. Now I want to look at another kind of definition. The ij cofactor of A is a number given as C sub ij, where that C sub ij is equal to negative 1 to the I plus j times the determinant of my matrix A sub ij, meaning my matrix that I get when I delete the ith row and jth column. So let's kind of look at the example we just looked at before. This was now my determinant of the matrix A that we had in the previous example, and we wrote it out using the first entry in our first row, and we want to multiply that by then the determinant of the matrix that I have left when I delete the first row, first column, and so that is then C sub 1, 1. Then plus 2 times C sub 1, 2 plus 0 times C sub 1, 3. So this is just another kind of notation, the ij cofactor, to write. And this was an example of a cofactor expansion across row 1 of our matrix. So now let's look at a theorem. This is theorem 1 from this chapter. The determinant of an n by n matrix A can be computed by a cofactor expansion across any row or down any column. So defining this ij cofactor, now we can look at another way to find our determinants instead of just the definition we previously looked at. And so we see this first formula gives us expansion across any row, and then here we have expansion down any column. And here's the way that we can kind of determine our signs. We can use what we call a matrix of signs to determine the negative 1 to the I plus j power. So basically, if you'll start with a plus sign always and then alternate minuses and plus signs from that point on, then you have a matrix of signs to know what sign needs to be in front of that entry. So we'll look at that in the next example. Here we want to compute the determinant of A using cofactor expansion down column 3. So we're going to go down column 3. So we want to find then the determinant of A. And what we're going to do is start with our first entry, which is 0, times then the determinant that we get from deleting the first row and the third column, which is 3, negative 1, 2, 0. And then remember my matrix of signs, this was a 3 by 3. So for my next entry, I have a minus sign going down. So we're going to subtract, and then my next entry was 2 times the determinant of the matrix that I get when I eliminate the second row in the third column, which is 1, 2, 2, 0. And then looking at my matrix of signs, the last entry will have a plus. So we have plus 1 times the determinant, and we want to eliminate the third row in the third column. So I have 1, 2, 3, negative 1. And now we'll compute those individual determinants. So I have here 0 times, I multiply 3 times 0, I get 0 minus a negative 2, which makes it plus 2, minus 2 times, now I have 1 times 0, which is 0, minus 2 times 2, which is 4, plus 1 times a negative 1 minus 6. So here I have 0 times 2 minus 2 times negative 4 plus 1 times negative 7. So we have 0 plus 8 minus 7. And so I will get 1 for my determinant. And if you recognize, this is the exact same matrix A that we did in the first example, and when we did our determinant using the first definition that we had where we went across the first row and expanded that way, we got the same value for the determinant of this matrix, so we got 1. And so this is just a demonstration that this does work. You can go across any row or down any column when you do your cofactor expansion to find the determinant. So bearing that in mind, it's nice when we have zeros because we can essentially eliminate some work for ourselves. And so what we're going to do is look at computing the determinant of this matrix A here. And remember that we can choose to go across any row or down any column. So I notice here that I have one non-zero entry in my first column. So what I'm going to do is I'm going to find the determinant of A by going down that first column. So I have my first entry, which is a 1, times the matrix that I get when I eliminate that first column and the first row. So I have 2, 1, 5, 0, 2, 1, 0, 3, 5. And now I'll have minus 0, which is my next entry, times the matrix that I get when I eliminate the second row and first column, plus my matrix of signs. Remember, I have plus, minus, plus, minus. Okay, so I have plus next, 0 times the matrix that we get when we eliminate the third row and the first column, and then minus now 0, which is my last entry, times the matrix that we get when we eliminate the fourth row and the first column. But notice that we're multiplying each of these by 0, so basically I can act like they're not even there. So I don't need to worry about the work on those. And so now I want to worry about finding the determinant of this 3 by 3. But again, we see that we have one non-zero entry in the first column, so I can do the same thing. So I have simply a 1 that I carry along, and now I'm going to worry about this determinant here. So I've got 2 times the determinant that I get when I eliminate that first column and first row, which is 2, 1, 3, 5. And remember my matrix of signs, I start over here. I have a plus, a minus, and a plus. So I'm going to subtract 0 times my matrix here from eliminating the second row and first column, then plus 0 times my matrix when I eliminate the third row and the first column. And notice again that these zeros, we can essentially eliminate them, so we don't need to worry about that work. So I'm down to now having 1 times then 2 multiplied by the determinant here, which is 2 times 5 or 10 minus 3. So what I have then is 1 times 2 times 7, which will give me 14 for my determinant. So there was a lot less work when we used the ones that had zeros. Now, when we have zeros, it's nice. But if there were not and we had a larger matrix, then this method is not practical because there's just a lot of computation and a lot of places for error. So we're going to look at some other ways that we can kind of make this shorter. And the first one we'll look at is some triangular matrices. Our first matrix is upper triangular, meaning we have zeros on the bottom and our numbers form an upper triangle. And then here's a lower triangular where our numbers are forming the lower triangle and we have zeros above. So we have theorem 2. If A is a triangular matrix, so we have either all zeros above the diagonal or zeros below, then the determinant of A is the product of the main diagonal entries of A. So in this example, we can look at this and notice that we have an upper triangular matrix. So we're going to look at the diagonal entries and we will take and multiply 2 times 1 times negative 3 times 4, and we will get negative 24 for our determinant. Now we could work this out just to verify, and notice with all the zeros that I'm going to start here multiplying 2 times the determinant that I get when I eliminate first row for first column, which would be 1, 2, 3, 0, negative 3, 5, 0, 0, 4. And we saw in the previous example that I can ignore the rest of the entries in that column because they're zeros. So now I want to take and find the determinant of this 3 by 3. So I have 2, then times 1 times the determinant that I get when I eliminate that first row and first column, which is negative 3, 5, 0, 4. And so now we have a 2 by 2. So I now have 2 times 1 times then negative 3 times 4, which is a negative 12 minus 0. So I end up with 2 times 1 times negative 12, which is negative 24. So we see then that this method is the same. We'll get the same value for our determinant.